Alright, in this video we're going to do some more antiderivatives, which I think people tend to find one of the most challenging things in kind of a Calc 1 class. So let's get started. So say we want to do the antiderivative or the integral of x over the quantity x squared plus 4. So to me this looks like kind of a u-substitution problem. So if that's the case, you want to first guess what u is. So a really good guess for what u would be is the denominator, which happens kind of frequently when you have a fraction that you have to integrate. So I make that as my initial guess, and now I'm just going to check. So I think what makes people uncomfortable about antiderivatives is that until you're good at them, you kind of do a lot of fumbling around. Like you make a guess, you see if it works. If it doesn't work, you try something else. And until this point in math, you're kind of like fed this notion that every approach you use is just going to work on the first shot, and that's just not the case. So I've made a u-substitution, u equals x squared plus 4, which would mean that du is 2x dx. I want to compare this to the original. So in the original I have an x and a dx, but I don't have a 2. So what I'm going to do is kind of move it over, get 1/2 du is x dx, and now I can straight substitute for everything in the original problem. So the original problem is going to become 1/2 du over just u. You might want to take out that 1/2 to get 1/2 the integral of du over u. And then this you should recognize is the natural log of the absolute value of u. So another thing that you'll run into is if you don't know the basic antiderivatives, you pretty much can't find any. So this is one you should recognize. We get that. You got to put in those absolute values. Sometimes you can drop them after the fact, but it doesn't usually hurt to leave them. So I'm going to just leave them in my answer here. And the original was in terms of x, so the final answer should be in terms of x. So there we go. Let's take a look at another one that looks similar but is actually different. So we want to do the integral of 2 over x squared plus 9 dx. So there's no x in the numerator this time, which makes it kind of entirely different. So, but you do the same thing, right? You guess that maybe u is equal to the denominator, so x squared plus 9. You find du is 2x dx, but now you run into a problem because when you're looking at what you have a 2 and a dx, but you do not have that x. If you don't have an x, there's kind of nothing you can do, which means that you just need a different approach. You can multiply in a number, but you can't multiply in an x. So I need a different approach. So what I'm going to do, usually when u-substitution fails, it's often arctan, so I'm going to try that. So I want to rearrange it so it looks like arctan. So I'm going to take a 9 out of everything in the denominator. So remember, taking a 9 out is the same as kind of like dividing by 9. So I'm going to get x squared over 9 plus 1. And then dx. So I can factor out the constants, and then I'm going to rearrange it so it looks like the arctan that I have memorized. Now I'm going to make a u-substitution. So I'm thinking that it's arctan, which means that x squared over 9 is actually u squared. So 2 over 9. So I'm going to make it x over 3 squared. So u is x over 3, and then du is 1/3 dx. I have a dx, so what I'm going to do is I'm going to make it 3 du is equal to dx. Now I can substitute for everything in the problem. So I have 2/9, 3 du, 1 plus u squared. So I can actually take out that 3, which cancels with a 9, and gives me 2/3. And this is basically arctan at this point. So the arctan of u plus c, but I know what u is. U is x over 3. So I want to finish the problem with x's because it started with x's. So there you go. That's another example, but they look very similar when you started out, right? The first one you had an x in the numerator, which made all the difference, really. If you don't have that, then you start thinking maybe it's arctan, maybe you can work it out that way. Let's take a look at another one. So this is a combination, right? So you might initially just go with u as the denominator, and then du is 2x dx, and that minus 6 causes a problem. So what I'm going to do is I'm going to break it up into 2 fractions, really, before I do anything. So I'm breaking this up. And this all comes with experience. You just have to do a lot of problems to figure out what you should do first, what's the best idea. So if I look at the first integral, it looks a lot like that integral I did before, where u would be the denominator. If that's the case, then du would be 2x dx, so there should really be a 2 in the numerator. So what I'm going to do is I'm going to use the approach of balancing, right? I'm going to multiply a 2 in, but at the same time divide by 2. So I'm going to have a 1/2 on the outside and a 2 on the inside. If I simplify that, I get back to 1, so it goes back to the original. But now I made the integral kind of perfect, which I'm putting air quotes around, which you can't see. it's perfectly the derivative of the natural log of x squared plus 25. So I balanced it out. Basically, I did the u-substitution without showing u-substitution, and I got that. And then I have minus 6. I'm taking 25 out of the denominator again. Give me that. And then I'm thinking this looks like arctan, so u is actually x over 5. So if u is x over 5, du is 1/5 dx, which means that I really want a 1/5 on the inside, and then a 5 on the outside, and then it's perfect on the inside, right? That's definitely the derivative of arctan of x over 5. So let's recopy, simplify this fraction. So that's going to simplify to negative 6/5. And then this integral now is just, it's a perfect integral because I balanced everything out, and then you get plus c. I'm going to do one more, which is kind of unrelated, but people run into it sometimes. So say we have a problem like this, which looks like it should just be really simple u-substitution. We're going to run into the same problem that we've run into before, though. We make u equal x squared minus 1, which means that du is 2x dx, and that x is a nightmare scenario for us. So u-substitution is not going to work. So on this particular problem, which looks so easy to begin with, what I really need to do is expand everything. So I'm going to expand, and then it's actually very easy. I'm just going to reverse power rule all the way through it. So 1/5 x to the 5th minus 2/3 x cubed plus x plus c. Alright, so that's just a couple of examples of antiderivatives. I hope you found it helpful, and good luck.